My pleasure to have, actually today, as I said, when we do our machine learning symposium seminar series, we do have a lot of external speakers. We also have some internal speakers, especially when we have an opportunity for somebody who has recently joined Georgia Tech, and it's been what, a year? Less than a year?
Since October.
Since October. Joined the faculty at Georgia Tech. And of course, Felix Hermann, I've got to spend some time with him over the last few months talking about it. Very diverse set of interests, and also just by the labels of the departments that he's associated with at Georgia Tech is significantly long. Earth and Planetary Sciences, Computational Science and Engineering, and even some
PCE.
other PCE, you name it, lots of departments and stuff. He used to have a great large operation around machine learning, at least the way I look at it. I'm sure that he does a lot of the stuff, but when the machine learning work shows up, that shows up on the top of my stack. Machine learning applied to lots of different technologies, including things like seismology. So I'm actually looking forward to hearing about that. With that, I'm going to just introduce you and get out of the way. Thank you.
Sure, thank you. Can everybody hear me?
Some of you want to move
All right.
up front, that'd be nice.
That's also always good to do. Okay, well, thanks for giving me the opportunity to talk. So this is not a very polished talk. There are even results that are like a couple weeks old in there. So I wanted to sort of give you a gist of what we do. There's not an enormous amount of math, but there are certainly a lot of connections to applications, and I will once in a while make a remark and try to connect it to things you know. There's a lot of material. Let's see how far I get. The key idea here is that there have been, in part driven, I guess, by machine learning, a lot of recent developments in matrix factorizations that allow us to do things that we could never hope to do. Whether this concerns the way how we acquire data, because I'm in seismic exploration, we use man-made sources to find out what the Earth looks like. And so these techniques can really have a major impact how you conduct that business. And then I will also talk a little bit towards the end, if I get there, on a very esoteric type of approach where we can now do things that you could never hope to do on any computer on Earth because the problem is too big. It's an enormously lifted problem. But by being very clever with linear algebra, you can actually do something. And so hopefully in the end of this talk you have an idea that linearized or linear algebra, randomization, compressive sensing, machine learning have a lot of offer a lot of tools to really make fundamental breakthroughs in applied fields such as seismic exploration. Okay, this work is not by myself. It's by a whole bunch of my graduate students. Some of them are in the audience. Some of them are postdocs. Okay, so just to give you an idea, and we aspire to these skills, and certainly in the first part of the talk, we will hit the sort of the order of skill. As I progress more towards the end, we're still in explorative stage, but we really design our algorithms with this sort of scale problems in mind, right? So in the field of seismic imaging, what we do, as I mentioned a little bit earlier, we have a source that sends acoustic energy into the Earth. It reflects, and then it's being detected by a bunch of microphones. And from those echoes we get back from the Earth, we try to make an image of the subsurface. Okay, so it's a very diverse field. It involves geophysics, but it also involves signal processing, a lot of mathematics that undergirds this. What makes it particularly challenging is that a typical image is 1,000 cube. So you have 1 billion unknowns. That is large. So that already makes it a bit different from big data. It's not only big data, but it's also big models, right? We typically collect 2 dimensions more data than we do the image, so that's about 10 to the power 15. And then for those of you who know about PDEs, we propagate waves over long distances, which has major numerical issues to do that. Right. So there's a lot of problems that hit you right there. Now, so what are we really doing is we are basically using a wave equation that is parameterized by m. Think of m as the speed with which waves propagate in the Earth. That's the unknown. And we want to obtain that as a gridded function of space from data we collect at the surface. And those, the velocity defines how waves propagate. So if we know a source, we can relate the source to a wave field through a wave equation. That's a discrete system of equations that discretizes a PDE that describes how waves propagate, right? And that is determined by m, so the sound speed that varies spatially determines how that system works. That's a big system. That's a system of billion by billion for one frequency, if m has a billion points. So that's a large system of equations right there. Okay, and then we collect only data at the surface. So, and we're basically trying to find an m that explains observed data, because of course we do explosions in the field to measure the response. And to solve this sort of problems, we solve a large minimization problem where we minimize an objective parameterized by this m that minimizes the misfit between observed data and the forward modeling that we do in a computer through f that is parameterized by m. And again, to remind us, these things are large. Things are also expensive, right? To collect a seismic survey sets you back between the $30 and $200 million. These are big exercises, take months and months with large crews. So this is not something you do in an afternoon. Okay. So, and the systems we solve, if we, for instance, solve it in the time domain, this is a large system, but there are direct links. If you look at this, this looks very much as an objective you would minimize in machine learning, right? So just label things different. So this would be, say, input, this would be training data, the m are parameters of a network, f is a network, and when we solve a PDE, you can think of that conceptually as a multi-layered network, except we have 10,000 layers. We don't do nonlinear operations between the different layers, but it tells you how big these systems are. Right, so these are really large systems of equations we have to solve just to link the physical parameters in the Earth to the observed data. Okay, so, and there are lots of associations you can have. So as I said, the forward model, you can think of that as a generative convolutional network. We do things called adjoint state, but that's backpropagation. We do simultaneous sourcing, that's sketching and stochastic optimization. So a lot of terms that may be well known in the machine learning community also apply to our community. We just call them differently, right? But the structure is the same, except that, you say, our variables are quite large. Although we have to say that the hidden variables in a deep convolutional network are also large, right? But I think if you want to think of the scale of the problem, we're really trying to learn 5K plus video, right? So we're not working on small little images. We work on really, really large data volumes. And so if you were to say, I want to use deep learning in this field tomorrow at scale, you have a problem at your hand, right? So this is sort of the, but that's a challenge, and that's why I'm thrilled to talk to this audience and to start working on this sort of problems. Okay. So I run a large research program, so I did a lot of work on optimization, compressive sensing. This is sort of an outdated, so it doesn't have machine learning yet, and it's MATLAB. We moved to Julia in the meantime, but it tells you a little bit of mind map of what the different things we are in the group. And we have to work on lots of different things to solve this problem. It's not like a nice, idealized thing you can just work on with a small team. You have a large team of people touching all these boxes in that mind map. Just to give you an idea what the output looks like, so this is sort of a conceptual model of the Earth where you have the velocity changes as a function of space. This is just 2D, but of course we want to go to 3D. And then typically what we produce are either a bit blurred images or sharp images at high frequencies that basically delineate where the Earth changes. We call this process, to generate this from the data, we call that migration. I will come back to that later. But the idea is to get very high resolution images, and for that you have to understand the physics of how waves interact with the Earth and collect data and try to figure out from the data what the Earth looks like. So it's a large inverse problem, but has a lot of HPC components because these things are so big. Right. Okay. So that was just, so now let's go to the research topic for today. And I will speak specifically today is how we can exploit low-rank matrix structure that underlies the data. Mind you, we're collecting data in 5 dimensions, 2 source dimensions, 2 receiver dimension, and time, whereas the image of the Earth is 3 dimensions. So there must be some sort of an inherent redundancy, and we're going to try to find ways to exploit that. And then, if I can, in the end, I want to talk about what we call subsurface image volumes which are a lifting of the problem. So if billion variables are not enough for you, in that case, it's a billion by a billion matrix. That's the unknown, right? So which you can never hope to form, but you can maybe work with actions with it, right? So that's, I hope I get there. So why do we care? Well, because we would like to reduce acquisition time. Acquisition is expensive. It has an environmental impact that you want to reduce. Can we be more clever how we acquire data? Reduce costs, which is very important these days because the oil industry with the low oil price is not in the best shape. But that's for everything. Data collection everywhere is expensive, perhaps, at least if you deal with sensors. Then there's massive amount of data, and that makes it also difficult to compute. So if you can find representations of your data that are enormously compressed and that allow you to extract subvolumes of it without having to form the full volumes, could have enormous impacts on how you process that data, because you take away a lot of burdens related to I/O. And then can you do things that you can never dream to do unless you're clever with your linear algebra? And let's see whether I get there. Okay. So just to, again, to show you a little bit what's going on. So this is a gridded velocity of the subsurface. So that's the property we're interested in. And as I said, that has typically about a billion grid points. And from that, with the wave equation, we can generate what we call shot records, which are basically single source experiment. This is the data that's collected by a two-dimensional array of receivers. And so the vertical axis is time, and you see here all these wavefronts coming in, and then this is the x and the y coordinates for your receiver. And then you do hundreds of thousands of these. So you collect a lot of data, and then of course the question is, can you map from here back to here? So it's a large imaging problem. Right. Okay. So they will soon hit petabytes in the data they collect. So you have to do a mapping from a 5-dimensional petabyte to something that lives, say, with a billion or something. Okay, to make things even worse, we are interested in basically doing a lifting where every grid point in the model that we're interested in generates a volume like this. So actually the unknown becomes a billion by a billion. So that's something that so you put almost like 1/5 of the Earth in a big Google matrix and it's dense, right? So that's fun. Okay, so we cannot form that explicitly. So let's start talking a little bit about what we do in the acquisition, because again, we need to collect data in order to create these images. All right. And so, as I mentioned, we are sampling a 5-dimensional wave field. It has one dimension for time, and then we have 2 receivers and 2 sources that walk at the surface. So it's a 5-dimensional data volume. And so we worked a lot on compressive sensing in the beginning and using transform domain techniques. And these are great if you are in 3 dimensions, but in 5 dimensions, the curse of dimensionality basically hits you, so these things don't scale. So all the fancy stuff we used to know from, say, harmonic analysis, things like curvelets, wavelets, all that stuff, unfortunately doesn't really work because it blows up in your face because the data is so large. So that prohibits the scale up to 5D. So can we exploit another type of structure to handle this sort of problems? Okay, so to do that, we're going to consider a 3D seismic survey as along these different coordinates, but we get rid of one coordinate. And we do that by taking a Fourier transform along time, and then we look at monochromatic frequency slices. Right? That is, you have 4 dimensions, 2 source, 2 receiver, but at one frequency, and then you look at different frequencies. Right? So, and these can be treated independently because the Fourier transform is orthogonal. Okay, so we call these things a frequency slice. Okay, so this is an example of a frequency slice. That's a small one, but it's still a dense matrix of 27,000 by 27,000. And that represents a small patch. This is sort of a post-stamp 3D seismic example, but that's already pretty tough if you will have to work with this stored explicitly. right? So we would like to work with this full matrix, and but you know that may not be possible. So one of the things we can do is to, and I will talk more extensively about that as we go on, is to recognize that if we organize the data in a particular way, which I will revisit in a minute, we can actually work in its factored form. So instead of working with this dense matrix, we recognize that if we organize matricize this four-dimensional tensor into a matrix, and we do that clever, that there is actually redundancy. And it's not so crazy that there's redundancy, because these sources and receivers look at the same Earth. There is fundamentally redundancy there, certainly if you don't touch too high temporal frequencies. So we can actually think in terms of a factored form, and then we only work with the factors, and we can then, without forming the full volume, extracting certain volumes that we need for the inversion. That is the imaging. I mean, is that okay? Okay, so what we're doing is, we're doing basically the Netflix matrix completion problem on steroids. It's a large, dense matrix, and so there's a whole literature on this. We worked with, in my group, but also with Ben Recht, who is now at Berkeley, who works a lot on machine learning type problems, and there's a whole bunch of papers that you can find online that deal with this. Okay, so what is key if you do matrix completion? And I will go through these, and then I will make the connection to how you have to rethink your seismic in a way to make it fit in this framework. Because if you just do things naively, it won't work. You have to be sort of clever what you do. And so you have to, first of all, try to find a representation of your data, read a matrixation of your rank 4 tensor into a way that the singular values decay fast. So how can you do that? That's the first question we ask. Okay, so we basically have to think about how to unfold a rank 4 tensor into a matrix, and there are different choices you can make. Right? So if you have 4 dimensions here, 2 source and 2 receiver, you can either put together source X and source Y, and that would be the canonical representation, and the same for the receivers, or you can do a permutation, because there are many different ways how you can matricize your data. So this is an example of a frequency slice, where that means you look at the data at one frequency, where I lumped together the source X and the source Y coordinate on the x-axis, and the receiver X and receiver Y coordinate on the vertical axis. And in here you see all these sort of different little experiments. That is basically a little part of a 3-dimensional survey. Right? And this is a zoom what these things look like. So you see these sort of oscillatory functions that decay away from the diagonal, because waves propagate away from the diagonal. Now this doesn't decay fast, these singular values. Whereas if you permute, so you lump together source X and receiver X, source Y and receiver Y, the singular values decay way faster. So how you organize your data, how you represent it as a matrix, makes all the difference. And that makes a real big difference. It makes whether your matrix completion works or doesn't work. And this is sort of where you, as a person in an applied field, have to understand why that's important and understand what you need to do, because nobody told us to do this. That's something that we came up with. Okay, so that's good. So we have a representation where the singular values decay fast, and that's a reflection of the fact that seismic data is redundant. Because again, we collect 5-dimensional data, and in the end we're interested only in a 3-dimensional Earth, and this data is generated by a 3-dimensional Earth, so that there is a low rank structure is not necessarily a big surprise. Okay, but that's not the whole story. We also need to think about sampling. And sampling we do not have a lot of control over, because we are dealing with a physical system. So the simple sampling I will talk about for now is where we miss certain sources or receivers. That is, we just didn't collect, we didn't fire a source somewhere, or we didn't have a receiver somewhere, right? Which is, either my boss told me I couldn't do it because it's expensive, or I just couldn't do it because there was a physical obstacle or something. Okay, what you want with the sampling, and that's an idea from compressive sensing, is you want your sampling to break the low rank structure. Then a rank minimization algorithm will give you potentially the full data back. That's sort of the compressive sensing idea we try to exploit. Okay, so if you are in a canonical representation, that is source X, source Y, receiver X, receiver Y, and we miss a source, we miss a column, right? If we had missed a receiver, we would miss a row. And missing rows or columns in the matrix does the opposite of increasing the rank. It decreases the rank. So this is the worst possible sampling you could ever dream up if you are interested in a matrix completion problem. And nobody ever tells you that, because the theoretician in that field to say, oh, we take uniform random samples, then we will never have this. But I cannot do that in the field. In the field, I miss a source and I miss it all the way, right? So this is sort of, I can't control that because of a physical system I'm working with. But if we go permuted, then it looks like we lose random blocks. And now the rank, or the decay of the singular values, you should say, is much slower. And therefore, a rank minimization scheme will stand a chance to get your full matrix back. So it's a simple trick where actually there's a free lunch. We have a representation permuted where the singular values decay fast, and the sampling is, in sort of loosely used terms, incoherent. It sort of raises the, or slows down the decay of the singular values, which is a good setting to be in if you want to fill in this matrix as if you took samples everywhere. Okay, so let me use techniques from convex optimization to solve these problems. So X, in this case, is the full data matrix, as you had samples everywhere. Then the curly A is, say, a mask that takes out, yeah?
So I have one question. Go back to, you can go back to the slide, or 2 slides. So, or go to the next, actually, would be better.
Yeah.
So, okay, so this matrix on the left that you're showing us piece of, that's what you're saying is low rank.
If it's full.
Yeah, if it's full.
Yes,
yeah, that's
correct.
I mean, is low rank really the best model? Like, isn't there some generalization of rank which would be more appropriate here? Because it's like not the columns that are related. Like, it appears the columns appear blocks, you know, and those blocks are what's related to each other. Like, there's some notion of like block rank that would be more appropriate.
Could be, although what we will show is in the recovery, we actually want to use information that extends over the whole area. So we consider the full object rather than locally. So what industry does, they think in terms of very little windows, 10 by 10 by 10 by 10. We think of the full Monty. And then we exploit the fundamental redundancies that resides in the data because we're looking at the same Earth. Right? So you may be able to fine-tune these things. And I will give you a little bit more pointers of where we're thinking theoretically.
Because that would be something which also would have some convex relaxation and it just wouldn't be nuclear norm anymore.
Yeah. So in the end, we don't do nuclear norms. Way too expensive. Okay, so what we do in order to deal with this, and now we make a, so anyway, this A, that models how you acquire data. So that knocks out things where you don't have anything, and B is you observe data, and you solve an optimization problem that finds amongst all matrices X, the one that has the smallest sum of the singular values, subject to that if you apply the sampling operator to it, you get your data. Okay, so now we make an additional step, and this is turning a nice convex problem into a non-convex problem. But we're forced to do this because we can never hope to really work with the full X. We can only work in a factored form. So we work in a left-right decomposition of that matrix where the L has a small rank, much smaller than the size of X. Okay. Now we developed a solver for this. There are some papers on that, but for the interest of time, I will go a bit quick. But we never compute the singular values. We work with an upper bound of the Frobenius norm by the factors for what the singular values are, because we can't even avoid doing any of that. Okay, so now that's nice, but you know, who cares? And also, you would like to know beforehand a little bit what should you do and what you should not do. What I did now is very, very qualitative. Can we go to something that's slightly more quantitative? Having said that, it's very difficult to come up with strong mathematical conditions that will tell you exactly what you need to do in the field, right? So that's still an open problem. That's the same thing with compressive sensing. It has beautiful theoretical results, but almost nothing translates to practitioners. Our matrices are not idealized. There's lots of things that just don't necessarily map. But there's one thing that I think will give us a little bit of a handle, that's the spectral gap. So to look at basically what's the connectivity of your samplings in the matrix, and that is a predictor of how well you think you can actually recover. Okay, so to remember, our goal is to find an approximation to X from noisy observed entries that live in omega, and the set of omega is much smaller than the set of X, right? So we have a restriction operator that X on X that gives us the samples, or a mask if you wish. And then we solve this optimization problem to get there. Okay, so there are a couple of things that you need to do. So first of all, a lot of the mathematics makes assumptions on how this omega is distributed. And typically people assume it to be uniformly distributed. But as I said already, that is not necessarily something we can do in practice. Another thing that you need is that you have to have the singular vectors need to be incoherent. So there are some conditions on what the singular vectors look like, how their energy is basically spread. The more the energy is spread, the better. And that is something we can compute, at least for the large singular vectors. Okay, so if we have uniform random sampling, then everything is nice, right? So that means we have a matrix. We only have axes in the matrix where what's white, and so if that's uniformly distributed, that's good. The other thing that we need is that our data looks sort of spread. So it should not look like this, it should more look like that. And from the seismic data that I showed you already, things are enormously spread. These are waves that propagate everywhere, so things are very incoherent. You're in a good setting where this would work. I know this is a bit hand-wavy, but I'm sure if you compute some of these things that you will be in good shape. The only thing what we don't have is this uniform random sampling where you have only access to a uniform random subset of entries in the matrix. We just don't have control over that in that way. So what then determines a good matrix, and can we come up with a metric that tells us beforehand how well matrix completion would be performing given a certain sample mask? And that's the sort of the aim here. Okay, so that has to do with connectivity. So you want basically your sampling to have connected submatrices, and maybe that alludes to what you're also mentioning with subblocks, right? And that is certainly true when you are uniformly sampled, then that happens. And so you can express this in terms of the spectral gap of the sampling mask. So if you have a sample mask that has a 0 where you have no data and a 1 where you have data, you consider that as a matrix, and you look at the two largest singular values. From graph theory, that tells you how connected these sample points are. And that's easy to compute. You can compute these two largest singular values on a very large system, not a problem. Okay, and then you can have either a small spectral gap or a large spectral gap. So that is that this ratio is either close to 1 or it's much smaller than 1. And what the theory tells you, it's good if it's much smaller than 1. So you want to have spectral gaps that are much smaller than 1. And we're working on, and this is work also with a student who is still at UBC, at theorems really making this much more robust. I want to just give you a flavor now how this works and what the effect of it is. So if you have a large spectral gap, that is, this value is much smaller than 1, then all submatrices are nicely sampled, and we can then expect better results for matrix completion. Okay, so let's start looking at the ideal case. So this is an example now of everything in the right organization uniformly sampled. So this is what we can never hope to do, but this has a very good spectral gap. Very small, that means there's a large difference between the first and the second singular value. And then we can actually recover from remarkable low sampling rates, right? We missed 95%. We have only 5% of the samples, and we can get a very good result back, something like 24 dB. Right, so, but that's idealized. We can never hope to do in the field, but it's good in the computer to at least check what these things can do or what they can't do. But there's, you make an error, so this is the residual. So you lose something. Just to give you an idea what these things look in the time domain, this is sort of basically a cube unfolded. So the vertical axis is time, the horizontal axis is receiver x, the vertical axis is receiver y, and then we look either in a cut through it like this or this. So this is a time slice. You look from above, and here you look from the two sides. You can see that you miss a massive amount of data. And this is what you get after you interpolate. So this is doing the interpolation for all the different frequencies, take an inverse Fourier transform, and this is what the data sort of looks like. And it's not perfect. You can see there's noise, but we get a lot of the aspects of the data from very, very low sampling rates. This is much lower than typically people can attain with compressor sensing when you work with transforms. And this is what the true thing is. So yeah, it's certainly not perfect, but at least we're getting there. Okay, so let's now look at the small case. What happens if we have a small versus a large spectral gap? So this is again is the original data, and then when we do recovery, when we have a large gap, so this is close to 1, or a small gap that's close to 0, and you can see that there's a remarkable difference in the recovery. It's the same number of samples. It's just how you select these samples as to make sure that there's a large spectral gap. So it's the difference between being clever and being not so clever, how you put your sources and your receivers in the field. And we can make a plot of that, and you can see as the spectral gap goes up, all the SNRs of the recoveries goes down, irrespective of what the subsampling is. And that's, so that confirms sort of the relationship. Now, of course, we would like to have that much more precise in the equations, but that's typically not so easy, but I think we have a chance here to do more than we have ever been able to do. Okay, so now that's all still idealized, and let's look now what the guys in industry do and see how that works. And so the most expensive and sophisticated way people acquire data in the field in marine settings is with so-called coil acquisition. It's a very clever idea. So instead of having a boat, so what you normally have is a boat that goes, and the boat tows an array of 20 kilometers long with a gazillion microphones on it, and then it pulls like 12 of those arrays. And then day and day night, it just tries to transverse a certain acquisition area. And in a traditional way, they would do it sort of this way, and then they have to return because the boat has to turn and they come back. And then there's really only good sampling in this direction and a poor sampling in that direction. So there's a poor, what's I call poor azimuthal sampling, because the boat has a preferential direction, how it goes over the area. So what people have proposed to do instead is random coil sampling. The boat goes into random circles, and the centers of these coils are randomly distributed. So they are doing random sampling in a very clever way that you can do with a boat that pulls a 20-kilometer long array, right? So it goes in very large circles, but the circles are slightly perturbed as it transverses over the area. So this is sort of where the sources are, so you can't see so much. So we're plotting what the trajectories is, where are the sources firing, and where the receivers are firing. So let me show you a zoom. So this is sort of what these coils look like if you look at the source. And that's not a nice periodic grid that people would like to have. So the question is, can we go from a mask like this and infill such that we have a equispaced sources? That's basically the goal of this whole matrix completion, is can you fill in what you missed? Because you missed stuff here, right? Whatever's white, you didn't put a source. And then of course you have to make also choices to how dense a fictitious source grid do we interpolate, to how a dense fictitious receiver grid do we interpolate. And for that we can again use the spectral gap to play around with matrices that have this mask, and then look how that all translates to how you sampled your sources and receivers, and how that translates then to a mask that you have to invert if you want to complete this data, as if you had, you know, infinite resources and you spent light years collecting the data, all the data. So we played around with this, and these are sort of the grid sizes for the receivers and the sources, and looked at the sweet spot to see which one would be the best for the best recovery. Now, unfortunately, we haven't verified whether these would really lead to better or worse results, because the computational efforts to recover a volume like this are massive. So you don't do this overnight. You can't run too many either. You could do it on smaller problems if you wish, but in this case we didn't. Okay, so what in the end it looks like is this is the mask if you organize the data in a non-canonical organization. And so the task now is, can you interpolate wherever things are white? And it misses a lot of data, and the spectral gap is not particularly good. So it's much better than doing other things, but it's not particularly good. And so, so we can't expect fantastic results, certainly not compared to uniform random sampling, where the spectral gap was significantly lower. So this is what the data looks like. So if you zoom in, this is the trajectory of the boat, and you can see sort of these different stripy things are the arrays of these receivers. So every boat carries like 12 receiver arrays, and you can see that it makes these crazy sort of trajectories, but mind you, this trajectory is in a weirdly organized data set. It's the permuted mask, if you wish. So the task now is from this to fill it in, right? And this is what you get if you fill it in. And so that is, what is remarkable about this, that we use information over the whole matrix to fill it in. That's different from what industry does. Industry works on little cubes in parallel and have no idea about correlations that exist over the whole survey area. And that, I think, is the reason why we can do this. We were crazy enough to think of this problem as in the full Monty, in the full sort of size, rather than already immediately chopping up things in little windows and try to play with that. So that, I think, is one of the carry-home messages. Now you can see that the residual is large, so it's not perfect. But if you look at the data, so this is the ideal data, this is the data we collect. So you can see you can miss whole parts of the data, and this is after your interpolate. So it's much less good than the previous one, but still it's remarkable that you can recover this. And actually this got the attention from industry. When we were in Houston, the company which is Schlumberger that does this coil sampling, they summoned us to come and give a presentation on this because they didn't know you could do this. Okay. So how are we doing on time? Okay, so yeah, all right. I may run a few minutes over. Okay, so what is cool about this, that aside from the fact that you can recover these data volumes, you recover them in enormously compressed form because you basically only work with the factors. So at the low frequencies, that can lead to enormous compressions. We worked only with 0.5% of this full data volume. So that from a compression perspective, you can, instead of carrying a truckload of hard drives with you, you can put your thing on a thumb drive. Right? It's a massive compression of what you need, and that may have a big impact on how we then subsequently work with this data to create images. So that will be a game changer because you can distribute the data over a cluster much easier than what you have to do now if you carry along all this massive full data. Okay, so I will skip this a little bit, but there's enormous compressions. The only thing that you need to remember is that these things work great for low frequencies. For high frequencies, it compresses less, and that is sort of understood theoretically why that is. So there's just much more complexity at high frequencies. Okay, so anyway, we can form data for inversion on the fly without ever forming the full data volume. That means I can give every node in the cluster access to the full data, whereas now they have to talk to a central huge database and extract the data, and that leads to an enormous amount of traffic. Now you have it all local. That will have an enormous basically impact on how seismic data is being processed. And I think maybe we can learn from this if we scale to larger scale problems in machine learning. Okay, so that's sort of the most down-to-earth topic. And now, in the next 15 minutes, I'm going to take you to something that's much more esoteric, but I'm going to try to give you a gist of why we care about this and why we can do certain things that you can actually never hope to do if you think about these things brute forcely. The industry is really brute force. I think Total has 600,000 core cluster for themselves. I think ExxonMobil has 2 Cray computers. These guys like to do things brute force. They throw a lot of money at it. But some things, even if you have the biggest computer on earth, you can just not do. And this is what this is. Okay. So there is some lingo here that you may hate, but I will try to connect it to some terminology that you guys may be familiar with. Okay. So let's first look at the physics of imaging, what's really going on. And I didn't talk a lot about that. That would be topic for another talk. But what we really do to create an image, we propagate a wave field in a computer from a source into a velocity model we think is representative. And that propagates, that's simulating waves. Okay? And then we also backpropagate. So here you can sort of see backpropagation, adjoint state, what we also know from convolutional networks. You go down and then you go back up. It's the same structure here. Right? We backpropagate the residual, basically whatever is at the receivers. And then we cross-correlate the 2 wave fields. Okay, so that's what, so you have a wave field in space and time, and a forward and adjoint, and you cross-correlate and you look at the 0 lag term. That's what your image is. And that's sort of what tries to represent here. So you have a source wave field, a receiver wave field, and then you correlate them. And if you look at the 0 lag term, that is basically looking at 0 offset. You look at the same point. But you don't have to. You could correlate the 2 wave fields and look at 2 different points. Now that's a lifting if you look at all points. So the complexity, your image now becomes as big as the image by the image, becomes quadratic, really large. But it has a lot of very interesting information that people are interested in. And that's why they compute some of it, but brute force. And we are basically saying, no, we can use clever sketching techniques to do these things without having to do things brute force. So we call this extended images because you map now the data to a 6-dimensional object, which is consisting of the 3 space dimensions times the 3 space dimensions. So it's a very large object. And so you can think of this as lifting. So for those of you who are seen, say, phase retrieval problems, people sometimes lift the problem. This is a lifting. Right, so you make the unknowns way larger, and that has particular mathematical advantages. Okay. So what people do is do this for a subset of offsets, brute force. Massively expensive because they have to store all these massive wave fields that have 1 billion variables each and cross-correlate them and then do different cross-correlations and store that. It's a mess. Okay. And so what we want to do is actually think of in terms of these image volumes as a function of all possible subsurface offsets. So every point in the subsurface generates a 3-dimensional volume in terms of the vertical and the horizontal offsets. That is the distance between 2 points in the subsurface. So that's a massive 6-dimensional object we're dealing with. Okay, so what we do now, we use clever techniques, and this is an observation made by Tristan van Leeuwen and Rajiv. Rajiv is an audience, that actually we can think of this object, never form it, but we can create actions of that object on vectors. And we can do that cheaply. And it's a little bit related, for those of you who went to Joel Tropp's talk a couple of weeks ago. We have access to sort of rank 1 actions of this matrix. And then we can play games. I'll speed up a little bit. There's going to be a little bit more mathematics here, but there's some math. So in the end, what in the end is going on? So mathematically, what do we have here? We have a source on the right, and we have the data residual here on the right, and this is the forward wave equation. So H is the wave equation, U is that forward wave field away from the source, V is the adjoint wave field, that is basically the receiver wave field propagating in an adjoint wave equation. Okay, so U and V are wave fields in space, and as a function of frequency. For now, I work frequency by frequency. Okay, so an image volume is the outer product of V and U. So that's quadratic in the size. So if V has a billion variables, then E has a billion by a billion. Right? And the different columns in V and U represent different source experiments. Because we have this for every source, we have a different one. Okay, so what conventional imaging does, it says, you know what, we're not interested in this whole object, we're interested in the diagonal, but that just means we take the Hadamard product of these different wave fields U and V and sum them. That's what you would normally do. And that gives you sort of the zero-lag correlation. But you could do something else. In E, there's much more. So think of it as a huge object, and what people only do to get an image is they look at the diagonal. And I'm saying, I want to look at off diagonals, or I want to look at that whole volume at whatever way I want to. And I'm going to be able to do that because this whole volume permits a low rank representation. So and that's the trick we're going to play, and we're going to only work with probing. So we're going to apply this volume onto probing vectors and then work from that. Okay, so let's look what this looks like. So say this is a very small Earth model. This is the image volume. So this is 1,000 by it's 100 by 100. The image volume is 10,000 by 10,000, right? Because it's quadratic, right, in the size of this model. If you look at the singular values, though, they decay enormously fast. So there's an underpinning low-rank structure here that we may be able to use. And so we do that by sketching, but we sketch with PDEs. So we play, and this is the trick here. If there's one equation of the second part you need to remember is this one, is if you, and it's just simple looking at the linear algebra, just playing with matrices, and then it stares at you. So what we do in order to compute the action of E on a sketching vector, say a random vector, we just have to invert the wave equation. We have to restrict it to where the sources are. We have to convolve it with the source, convolve it, or correlate with the source, convolve with the data, inject back at the receivers, and propagate again. So all these things you can do consecutive in the computer. You never have to form the full E. So that's cool, because now we can try to find out from probings what's the range of E, what's the range space of E. And we can do that by probing it with a limited number of random vectors on the right-hand side. And then we can do a QR factorization. I have to apologize for the notation. We just run out of symbols. So Q means, in this context, a source, and in this context, it means the Q of the QR factorization. But changing the notation makes everybody also, I think I have to play with fonts or something. So it's hopeless. So this is what I meant with, it's not a polished representation yet. Anyway, we can work with actions of E on Q and with Q, and that contains all the information you have to have in order to work with a large object like this. Okay, so let me see. I should really speed up. So let me just show you quickly what we can do as a randomized SVD. So when you have these actions, you can basically compute this QR factorization and then use this Q and EQ to form basically a low-rank SVD approximation of that large matrix. Right, so that's this guy. And from that guy, we can form left-right factorizations by simple lumping the square root of the singular values on the left and the right. Okay, so now this gives us an alternative formula for imaging. Right, on the right is this old formula we had, and on the left we have now something that is based on this matrix factorization of this ridiculously large object. And you can ask yourself the question, which one is going to give us a better image if we are only allowing ourselves to work with a very limited number of probings, or basically wave equation solves. I think I'm losing everybody, but I'll show you an image and then we're done. So in a way what we're doing is either we put a sketching on the data, which basically means we sandwich a matrix here in between, that's WS transpose, That's basically a matrix that contains basically crosstalk, because these are Gaussian matrices. Or you probe basically on the right and then work with these vectors. And with the same amount of PDE cost, we're going to basically compare these two images. So the amount of computational work is the same, but we're just being clever with doing fancy linear algebra tricks versus doing things brute force. That's basically what we try to show. And what is motivated by is that if you look at the decay for the singular value of the data versus the decay of the singular value of the image volumes decay much faster than the data. So a low-rank approximation of the image volume is much better than the low-rank representation of the data. So that's the key idea here. So these are the probing, so I will skip this and just show you some results. So I will show you also what people care about. So you may think that this is all very subtle, but this is the difference between finding an oil reservoir or not. So this is only with 10 probings, either the conventional way or the new way. Where are we? Sorry. So this difference, and you need to look carefully, you see certain reflectors popping up that are not existing in the conventional way. Particularly the steep events here, that's typically where the oil reservoir is. That's what people spend a lot of money on. And you can do this, same amount of work, same amount of PDE solves, just being clever with your linear algebra doing this. And this is when we increase the number of probings to 100, then there's still an enormous difference. You can see certain reflectors coming up that didn't exist in the other approach just by doing these sort of smart randomized linear algebra tricks. Okay, so I think that's it. I want to leave it here.
Questions? Justin. So I have a very high-level question. Actually, can you go to like the first slide where you still have this like A minus 1n? Or...
The first slide of the second part, or what?
No, the first part. Yeah.
The first, not the first. So you need.
Like when you're setting up the inverse problem at the very beginning of the problem.
Oh, yeah.
All
Okay.
the way of equation.
Okay, yeah, sure.
So,
This
yeah,
one,
so,
yeah.
Okay, so I understand very well how this comes about when you're trying to cover a velocity field.
Sure.
In acoustics and
Sure.
maybe in some other way.
Sure.
But like what other classes of learning or signal processing problems have this form where you're looking for like a parameterized matrix over a family of parameterized matrices that themselves are trying to solve another system?
Well, it is so. This is so all PDE problems where you're linear in the source has that form, right? So we write it deliberately like this because we're linear in the source.
So you're saying for every parameterized PDE you can write like this?
If it's linear in the source, yeah. So a whole class of inverse problems would pertain to this, not only waves. Yeah. But this shape, I mean, this form looks very much like a CNN. You have a parameterized convolutional network. You have training data, so D is the training data. For now we assume Q to be known, but M are the parameters of your network. And people use stochastic optimization techniques to solve that. And then they use backpropagation. We use also backpropagation. We call it adjoint state. So there are a lot of connections. So we looked a lot at solving this problem using stochastic optimization techniques, but that's a separate talk. But since this is a machine learning seminar, I thought let's make there are connections everywhere. Except our problems are large and we can't do tens of thousands of iterations. We can do 100 maybe.
So building on just that specific observations, I mean, we can use machine learning for optimization. We can use machine learning for a lot of things. But one of the other things we can use it for is doing large-scale prediction.
Sure.
That kind of stuff started showing up in this world. Now we can start predicting.
Well, so in a way we're also in the predicting business, but we are fundamentally different than where you guys are. So if I have to correct M, I can predict every data for that area. So that's a predictor, right? But what we really care about, we don't care about predicting the data, we care about M. So our parameters, say the parameters of your network, are the object of interest. So we need at least part of our parameters to be interpretable. Whether you augment this with learning techniques that are hidden variables, that's exactly what we're looking at in my group now. And then we don't care whether we interpret those variables. But in principle, we do really care. M is the object of interest.
So one of the other things which has started happening, and I'm not a big fan of it in machine learning, is this. We're going to get a lot of data. We're going to ignore the physics and just use the data
Sure.
to model the phenomenon, and now basically, quote unquote, learn.
But I can learn the data, that's not the problem.
So is
I
that
want something that gives me an image. Okay. The image is what I'm interested in. So if you happen to, so in a way you can think of it, we parameterize the model by the wave equation, and we say the coefficients of the wave equation is something that gives me tangible information. But you could ask other questions, right? You could say, I don't want to have an image of the physical parameters of the Earth. I want to know at this depth whether there's an oil reservoir or not. And then you may do a black box one, but then you have to train it with a heck of a lot of examples where you have data and you know there was a reservoir there. Then maybe you can do that.
Now you do, of course, have huge amounts of temporally varying data, right? You have data at a certain time.
Yeah.
And using that, you can now start extrapolating.
So I think you mean, the time of the waves or different experiments?
Different timelines and being able to use the timelines of different things, not just the data collection that happened today.
Yeah, so that we call 4D or time lapse. Yeah, so we look in that. We haven't looked from the machine learning perspective of that. But then you add another scale of large, right? But so where I see where the opportunities for machine learning are is this is based on a presumptuous physicist who thinks he owns the physics, understands the physics. That's basically A. The geophysicist believes that's true. I don't believe it's true. So where can you use machine learning to make up for the fact that the wave equation doesn't describe all the physics? And then you have a bunch of parameters you don't necessarily care about. But some of them you should, because otherwise you can't interpret your results. And that's, I think, also the difference between machine learning, perhaps, sometimes, and inverse problems. With inverse problems, we really need something that we can interpret.
Supposedly going to beyond system identification, right? System identification, inverse problems, where now you're defining the best possible parameters. Now, sometimes machine learning goes further into nowhere land, but sometimes, in case of categorization, the data is never sufficient. You really have to start modeling the phenomenon in different possible ways.
Yeah. Well, so I believe that I'm a big believer in physical constraint networks. So you can think of, again, networks that have both. So, but I don't believe throw it all out, it's all black box and CNNs are going to do everything. I don't think so. But I don't believe that the wave equation is going to do it all either. Right? So that's the sweet spot to sit in between.
Great. Well, thank you so much again. I learned a lot about this.